Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. Roy Castle used to end every episode of Record Breakers by singing "Calibration's what you need." Okay, he actually sang "Dedication's what you need," but since both are needed to run a DSC properly, I don't think he'd mind me changing his lyrics slightly. So, if you haven't guessed by now, in this video we're going to look at calibration of DSC instruments. Calibration is a critical step before any DSC measurement is made, and indeed, any analytical measurement. If you don't calibrate your DSC prior to running an experiment, you cannot be sure that the temperature and heat values you measure are accurate. Also, when you run experiments at different heating rates, and I hope you know from earlier videos why that's important, you should calibrate at each heating rate. Calibration is quick and easy. So get yourself a reference material. Mine would be coffee, if I were allowed. And let's make a start. You may not have thought about it, but any analytical measurement is just a somewhat meaningless number, unless it can be compared with a reference value. Let me give you an example. How tall do you think I am? Difficult, that, because I'm always sat down in these videos. I'll tell you, I'm about 12 times taller than the plant pot I have in my garden. Does that give you a feel for my height? No, because you don't know the size of the plant pot I'm referring to. On the other hand, if I tell you that I'm 1.78 meters tall, hopefully you'll have more of a feel for how tall that is. That's because I gave you my height in a unit, meters. I chose meters because that's the SI unit of length, but I could have used any unit that we all agree on. And that's the key point. To measure something, we have to use units. And when we do that, we are simply saying that our thing is some multiple of another thing. I'm 1.78 multiples of a meter, and we know what a meter is because some clever scientists have defined it, and many other units, of course. And while I'm here, I shall note that SI stands for Système International, or International System, and is a standardized set of measuring standards that we all agree on. I think I might do a video on SI units at some point, so stay tuned for that. What physical properties are important in a DSC measurement? Temperature, clearly, as we are heating or cooling our sample. Power, because that's what we are supplying to our sample and reference materials. And heat, because we want to know the change in heat content when our sample undergoes a phase transition. The more observant among you might also say mass, because we need to know the sample mass in order to determine the heat change in per gram or per mole units. And while I'd agree with you, I would consider that mass is not measured by the DSC, but by the analytical balance used to prepare the samples. So, the principal properties we are concerned with are temperature, power, and heat. The SI unit of temperature is the Kelvin, although we tend to use degrees centigrade in everyday life, unless you're American. And that is what I've been using throughout the series. The SI unit of power is the watt. And as I noted in a previous video, 1 watt is equivalent to 1 joule per second. The SI unit of heat is the joule. So really, all we need to concern ourselves with in DSC is measurement of temperature and heat, because we can derive power values if the instrument keeps good time. And I'm assuming here that the electronic circuitry on the instrument does keep good time. We know what the units of temperature and heat are. But how do we go about checking that the DSC we are using is measuring these values accurately? And while we're on the subject, we're concerned with accuracy here, not precision. I have a video explaining the difference between accuracy and precision if you're not clear on that, the link for which is in the description. We check accuracy by measuring reference materials that have very well characterized transition temperatures, typically melting transitions, and or heat changes, again, usually a heat of melting. So, for instance, I can tell you that indium, when pure at least, melts at 156.6 degrees centigrade. Therefore, if we put a sample of indium into a pan and heat it up in a DSC, we should see a melting endotherm with an onset temperature of 156.6 degrees centigrade. If we note a different value, we need to correct the temperature values being recorded by the instrument, because we know the temperature at which our indium sample melts. In other words, because our indium sample is known to melt at a particular temperature, we can use it to adjust the temperature values being recorded by the DSC. Now, you might raise a couple of questions at this point. Why would the DSC measure the wrong temperature? And what would happen if the sample of indium was not pure? Those are excellent questions. Let's deal with the instrument temperature first. We set up the instrument to change the temperature of sample and reference at a particular rate. And those are the data that are plotted. But we should remember that the instrument measures sample and reference temperatures with thermocouples, and these are not placed within the pans. Rather, they are located under the pans and are in fact measuring the temperature of the furnace. We assume that the sample and reference temperatures are the same as the furnace. But in practice, there will be a small temperature lag because it takes time for the energy being supplied by the furnace to reach the sample and reference. For instance, the energy must pass from the furnace to the pan and then from the pan to the sample. The reference is usually an empty pan. Each of these transfers of energy takes time and causes a temperature lag. If we consider our indium reference material, then it will actually melt at 156.6 degrees centigrade. But because the temperature of the sample will be lagging behind that of the sample furnace, our data will appear to show melting at a slightly higher temperature. By using a reference material with a known melting point, then, we can determine how big the temperature lag is. When we calibrate the DSC, we essentially determine the size of the temperature lag and correct for it. So if, for instance, the sample is lagging 1 degree centigrade behind the furnace, it will appear to melt at 157.6 degrees centigrade. The instrument temperature is ahead of the sample, remember. And we subtract 1 degree centigrade from all the data points. This is also one of the reasons why you should calibrate a DSC at each heating rate being used. The faster the heating rate, the bigger the temperature lag between the sample and the furnace. So the amount of correction gets bigger with faster heating rates. How big is the temperature lag? Well, in an earlier video, I showed you some DSC data for indium melting at 2 heating rates. These data, in fact. And I noted that the onset of melting was the same, irrespective of the heating rate. What I didn't show you were the data before I calibrated the instrument. So let me do that now. These are the raw, uncorrected data from the instrument. And you can see that now both sets of data are displaced to the right on the temperature axis. Neither set of data shows indium melting at 156.6 degrees. Rather, both show melting at a higher temperature. And the faster the heating rate, the higher the sample appears to melt. This is the temperature lag in action. The other question related to the purity of indium. What happens to the melting points of materials that are impure? Do you know? The more impure they get, the lower the melting temperature. This is why salt is added to frozen roads and pathways. The salt makes the water impure and lowers its melting point, so it turns to water at temperatures below 0 degrees centigrade. I think you might see, therefore, that using an impure reference material would be very bad indeed. We would expect that it is melting at a particular temperature and correct our DSC data in response, but actually the melting temperature of the reference is wrong. To make sure that doesn't happen, we usually calibrate DSC instruments with reference materials that have been tested to make sure they are very pure, usually around 99.999% pure. They are called Certified Reference Materials, or CRMs, and can be bought from instrument manufacturers or suppliers of analytical standards, such as NIST in the USA and the Laboratory of the Government Chemist in the UK. One last point about temperature calibration. Should you calibrate with just one reference material or use more than one? That, of course, is a leading question. And the answer is you really should use more than one. To see why that is, consider what we are trying to ensure. We want to know that the sample temperature is the same as the furnace temperature across the entire experiment. If we calibrate temperature with indium, then we know at 156.6 degrees centigrade the sample temperature is correct. But what about at 90 degrees centigrade or 200 degrees centigrade? We don't know. We assume that the temperature lag is the same at all temperatures, but it may not be. Hopefully, this graph will make that point clear. So, we really should calibrate our DSC at several temperatures. If we do that, it's much more likely that the temperature values will be correct over a wider range. That is why a range of reference materials are available. You can see on the screen the most commonly used, and it would be good practice to calibrate with at least two of these widely spaced over the range you are making your measurements, to make absolutely certain your DSC is to be trusted. Trusted on the x-axis at least. The other property we need to calibrate for is heat. Remember that if we calibrate for heat, then we automatically calibrate for power. You'll be unsurprised to know that the principle for heat calibration is the same as that for temperature. We select a material that undergoes a transition with a known change in heat content, then measure the area under the curve for that transition. If we divide one value by the other, we get a constant of proportionality that we can use to correct our measured data. A commonly used phase transition for heat calibration is melting, and handily, the heat of fusion of indium is very well established, 28.6 joules per gram. You can calibrate for heat with any certified reference material with a well-established heat of fusion, but indium is the most widely used, because by using indium, you can calibrate for temperature and heat in the same experiment. Last point, assuming you're still with me, you should be able to see that you should also calibrate for heat at each heating rate you are using, because, well, you tell me. Have a think. Because peaks get taller and broader as the heating rate increases, so the area will change. And this will mean we need to determine a constant of proportionality at each rate. Right, I hope that makes sense. In the next part of this series, we'll pull all this information together and look at the principles of good experimental design. The basic stuff that you should consider before running your sample to get the best data. Hopefully, I'll see you for that. If you could hit the like button and consider subscribing, that would also be great. Otherwise, thank you so much for watching, and I'll see you again soon.